So let us continue with example 1, just make it a bit complicated and call it example 2. Suppose that now A, which is a long-running CPU intensive job, gets, a new job arrives. B, which is a short-running interactive job, we don't have any clue how long B will be, because MLFQ does not make any assumptions on how long a job will run. So it will start at Q2, because this is the highest priority queue, basically thinking that, well, it might be a short job, so I start at Q2 when it arrives. So A has been running for 100 time units, and then B arrives, gets scheduled right away, because, well, we assume it's a short flow. Sorry, it's a short job, and then it runs. And since the time quota in this example is 10 milliseconds, then after 10 milliseconds you demote it from Q2 to Q1, and you run it again for 10 milliseconds. And after these 10 milliseconds, if it has finished, then fine. Then you go back and start running job A again. If it does not finish, then it will get demoted again and go to Q0. And once in Q0, both job A and job B will alternate using round robin. So this is very neat because, well, in this case we do not make any assumptions on how long a job is, and it looks like it is actually working. And if we have IO, then according to rule 4b that we just stated, then this is what will happen. You will basically have a job running in Q2. Well, A arrives first, and or A and B arrive roughly at the same time. Then, well, actually, sorry. So A arrived a while ago. It's a long-running job. B just arrived, but it's an interactive job. So B kicks out A, starts running, but then it blocks on IO, and during the period that it is blocking on IO, A, which is in Q0, can run now because there is no other things to do in the system. So it runs until basically the interactive job B comes back to life because it has all the data it needs. So now again B gets scheduled again, and A stops, releases basically the CPU for B, and it goes on and on basically with whenever job B is waiting for IO, A can run. And, well, now the MLFQ approach that we thought of, the first one, will keep B at the highest priority because B keeps releasing the CPU. It never exhausts its CPU quota. And unfortunately, this approach have some major flaw. Can you think of one? So the first problem with this approach is the problem of starvation. There are too many small jobs. If there are too many jobs that basically yield the processor for IO. So suppose that there are like 1 million jobs on Q2. Okay, very tiny, very small jobs. Then they will definitely feel the time slots between the different IO operations, which means that anything on Q0 or Q1 will never run. And this is called starvation. It's basically when a process or a job is basically never scheduled because, well, there isn't enough space for it. The second problem is that a smart not user, but rather a smart program can actually try to game the system. And that is basically by, for example, trying to divide the operations it does in such a way that it's always less than the time quota that for the highest level queue, but it doesn't really go and do any real IO operations. It can just yield processor and then acquire it again. Yield, acquire, yield, acquire. And then basically the system has no way of knowing if, well, if this IO is actually needed or if it's just for gaming the system. So another approach to actually solve the MLFQ problem is to have a priority boost. It's a very simple idea, and that is basically after some time period S, you basically move all jobs in the system to the topmost queue. So this solution actually solves the two problems because anything that was on Q0 will jump on Q2 and will be scheduled and every S time units. This way, you're actually guaranteed that no process will be starved. Every single process will have time on the processor because it will move to the top queue after S time units. Second, if a CPU bounded job has become interactive, basically if a job changes its nature and was stuck in Q0, all of a sudden now it can move up the queues and become again in the highest queue. So it gets this priority boost. So in that case, you will basically, sorry. So black is your is the first job to arrive, and as you can see, you basically start running at Q2, and then you get demoted to Q1, then you get demoted to Q0. In this case, you'll just basically Q2, Q1, Q0, and after some predefined time, you will get a priority boost. And then this happens again, and then priority boost happens again, and priority boost until basically the job is done. The main problem with this is when do you basically do the priority boost? This is actually a general problem in computer systems. Many systems are built with what people call voodoo constants. I actually noted that at some point that there are, if you go through the Linux kernel, you'll find profanities, you'll find basically numbers that are like, we have tried all the other numbers that we could think of, and this is the only one that worked. And that is not neither engineering nor science because, well, you have something that works, and you're not really sure why when I increase that number by 1 or decrease it by 1, it doesn't work. So we have a lot of these voodoo constants in systems, and we want less of them. So this has been an issue, and thus this third attempt to actually fix these rules is to actually fix the rules for A and for B with no boost, no voodoo constants, or anything. And the way to do that is by using better accounting, where rule 4 gets updated to once a job uses up its time allotment at a given level, regardless of how many times it has given up the CPU, its priority is reduced, i.e., it moves down 1 queue. So in this example, it will actually not, I mean, the MLFQ will not just have priorities, but will have different time allotments at different queue levels. And with this protection in place, even if you game the system for the first few time units, you will use all your time quota at a given queue, and you will be demoted.